Okay, today we're talking about Chapter 3, Section 5, linear correlation and regression. Right, so we continue our talks about looking at data and, well, plotting graphs, and today we're talking about, obviously, linear correlation and regression. So looking at this, the very first part here, so as a final question on the math exam, a group of students were asked how long they studied for the test, rounded to the closest 10 minutes. So after grading the test without giving away any identifying information, the instructor presented the following set of data. Of course, we see our set of data here. And the instructor then asked the class if there was any relationship between the time spent studying and the grade received on the exam. After some discussion, the instructor showed the students the corresponding scatter plot and asked the same question. So let's first look at this chart here. Well, first of all, knowing the context is obviously really good here. So the context being time spent studying, and then the grade on exam. So you would think, context-wise, the more you study, the better you'll do. And if we look here, just first glance here, it looks like everybody that spent over 100 minutes studying scored pretty high. At least got an A, at least a college A, right, with that 90 there, right? So somebody spent 40 minutes, got 70. 40 minutes with 70. 60 minutes with a 60. I don't know. So, I mean, we can kind of draw a little bit of conclusions from that. All right, but now let's look at the scatter plot that the teacher presented. And then, excuse me. And then from looking at the scatter plot, we can see more of a correlation here, right? So we can see that it looks like, and of course, uh, the horizontal axis is the time spent studying. So as we go out further to the right, it looks like we're going up higher on the grade on the exam. And of course that makes sense, right? The more you study, the better you'll do. Right. So next we're going to talk about some definitions uh, regarding correlation. Of course, you've probably heard the word correlation a lot in your life, and we're going to just really define it a little bit better in this particular section. Although, I mean, you probably already have a good definition for it. But let's go ahead and define it real quickly before we actually look at the graphs, I suppose. I'll just do this thing a little backwards here. So correlation down here. So when a data set is presented in a scatter plot and there appears to be linear pattern there appears to be linear pattern, oh whatever, and there appears to be linear pattern to the data, we say that the variables represented by the data are correlated. Okay, so that makes sense. An upward trend, of course, when we say upward, we're talking about a positive slope, right? We've talked about that before. An upward trend in the data indicates a positive correlation, and a downward trend in the data indicates a negative correlation. And we can see a negative correlation going down here. Sometimes it might be a little bit hard to see, but I mean, you can kind of spot it, right? And then you have no correlation. There is nothing you can draw, no conclusion you can draw from a plot like this. Okay, so example one. This seems pretty darn easy, but let's go ahead and snip it and check it out. I think this might be one where I should just put right on top of one another because I'm not really working anything here. Alrighty, so example one reads, determine if the data set appears to have a positive correlation, a negative correlation, or no correlation. We're obviously having a positive slope here, right? We're going up as we're moving to the right. So this is obviously a positive correlation that we see here. So hopefully all the test is those questions, right? That's pretty easy. All right, next we'll be talking about correlation coefficients. Okay, good. Ooh, that's not what I want. Let's try that again. Hmm, that's unfortunate. I'd like to fit this on one page. Maybe I can make it a little smaller. Okay, so I guess that button doesn't work. Okay, so we'll just deal with it. Oh no, I made that smaller. Hmm. that's an issue. There we go. All right. Disaster averted. I had no idea what I did, but I'm really, really glad we were able to correct that. All right, so did I put no? Okay, good. Okay, so maybe we can try to stack this. Yeah, I think it fits. Yeah, there we go. Alrighty, so let's talk about our correlation coefficient. So to specify whether the correlation between two variables is strong or weak, we use a value called the correlation coefficient. And we denote that by the letter R. So the value of R ranges from -1 to 1 inclusively. Uh, the correlation coefficient is positive for variables that have a positive correlation and negative for variables that have a negative correlation. Okay, so all this makes sense so far. The stronger the correlation, the closer R is to either 1 or -1. For variables that have a strong positive correlation, R is close to 1. For variables that have a strong negative correlation, R is close to -1. Variables that have a weak correlation have a value of R that is close to 0. Okay, so we're going from -1 to +1. And so the correlation coefficient known by R we see here. So this is a strong positive correlation. So our R is going to be greater than 0. This has a strong negative correlation. So our R is going to be less than 0. And down here, we just have an X, right? There's no correlation here. And so obviously we're going to have an R, okay, there we go. An R closer to 0. I don't think it actually says it. Let's see. Okay, it doesn't put it in definition, but we have an R closer to 0 that has no correlation. Okay, so looking at example 2, determine whether a data set with a given correlation coefficient has a positive correlation, negative correlation, or no correlation. And of course, I snipped the solutions here, but I mean it's not abundantly hard to figure this out. When R is equal to 0, we know that there's no correlation. When it's negative, we know that there is a negative correlation, and when it's positive, we know there's a positive correlation. Right? Pretty easy, right? For negative number, negative correlation, positive number, positive correlation. And of course, the solution that the book gives corresponds with that. All right. We're gonna skip. We're not gonna skip it, but we're just gonna snip this part right here. We just talked about if something is exactly 1 or exactly -1, we have what's called a perfect correlation. And of course, we have our examples here. Whenever we have R is equal to exactly 1, we have a positive correlation. We see that we're going up. Whenever R is exactly -1, we have a negative correlation, and we see that we're going down. Okay, so again, positive correlation, positive slope, negative correlation, negative slope. All right, so let's get into modeling data. Yeah, I think this would need to be snipped here. It's all pretty good information. And while I do hate reading off of the text, of course, as you know, I've mentioned that plenty of times before. Sometimes it just needs to be said. And also sometimes the textbook, the authors of the textbook, have a better understanding of what the students need than I do sometimes. Okay, so I don't know if I'll be able to fit this. It's gonna be close. We'll see. Okay, so maybe we can put that down here. Over here? No, right here. Okay. Alrighty, so starting at the top here. So we looked at the time studied versus the grade earned, and we said, it looked like there was a correlation between, if you study more, you get a better grade. And of course, we saw that with having a positive correlation here. So, let's see. Now we can go here to linear regression. So, linear regression is the process of modeling the linear relationship between two variables. Interesting here. The term regression. Whenever we think about regression, we think about coming back, right? I was actually I was reading some comments talking about a very good quarterback in the NFL. His name is Patrick Mahomes. Very good quarterback, unbelievable talent. And somebody in the comment section said, what was it? Maybe it wasn't regarding him, but it was a joke. You know what? I don't know. My point is this: the comment said maybe they're progressing to the mean, right? And somebody came in and corrected him and said, no, it's still called linear regression. That's because that is the process, right? It doesn't mean that you're actually falling back. It just this is the process is linear regression, and hopefully you followed along with that with that statement. I was all over the place on that one. Oh well. Anyways, so using two data points from the data set, we can find the equation of the line that passes through those points and see how well that line fits the rest of the data in the scatter plot. So we'll illustrate this using the data points that corresponds to the highest test score and the lowest test score. So first find the slope between the 2 points for the highest test score and the lowest test score. So our highest test scores are 120 and 100, and my lowest test scores were 30 and 50. So we're going to find the slope between them. And if you recall, we have these 2 points. Let's see. Okay, if I misrepresented that. The first number is the time spent, and the second number is the grade. Okay, so we're finding the slope between the 2 points for the highest test scores and lowest test score. The highest test score being 100, the lowest test score being 55. The student spending 120 minutes on studying to get a studying to get a 100, and the student only studying 30 minutes to get a 55. And if you recall, the slope is just the change in y over the change in x. So 100 minus 55, or actually they do it backwards. That's no big deal. 55 minus 100, and we got negative 45. 30 minus 120, we got negative 90. And then negative over negative is a positive, and of course 45 over 90 reduces to 1/2. So we have a slope of 1/2, and of course we see that here. If you recall this this equation, this form, we call that the slope-intercept form, because we put the slope here first and the intercept here second. Anyway, so recall that we can determine the point slope form for the equation of a line using the slope and point of a line. So in order to generate this equation, we use the point slope form. Okay, and again, the point slope form is aptly named because, well, you use a point and you use a slope. And so since we got the slope, we're just going to use either of those points, and we end up generating this equation here using the point slope form. And we can see that we have, a pretty decent equation model for time spent studying versus grade earned. Alrighty, so next up, it's our turn to do a little bit of computation here. Alrighty, so the problem reads, use the given points to determine the point slope form of the equation that represents the data set for the time spent studying versus the grade earned. We're going to graph the line of the scatter plot of the data set. Okay, so I'm gonna do the computation, but I'm just gonna rip the scatter plot, okay? Because again, it's just I have that blank slate. It's kind of hard to go around scatter plotting, but we will work on and create this equation here. Okay, so first things first, we'll do okay. So we're wanting to find the slope of this point right here, or of these points rather right here, the slope of these points. And so I'm gonna do this. We're gonna do A here. We're gonna just go 90 minus 70. Again, this is the y values. Okay, 90 minus 70, and then 100 minus 40. All right, things worked out perfectly here, so I don't have to worry about negative numbers. So we have 20. Let's fix that too. We have 20 over 60, or in other words, 1/3. Okay, so we have 1/3. Now we're going to use the point slope form and figure out the equation of that line. So the point slope form, again, let's go ahead and rewrite this just in case you have forgotten, or just a nice little reminder. It is y minus y1, and that's equal to m, again our slope, times x minus x1. Okay, And in this particular example, let's see which doesn't really matter which point we use. I mean they're both pretty easy. But I'm just gonna use the 190 just for fun here. So we're gonna have y minus, and my y1 there is a 90, so y minus 90, and that's actually let's do this. Let me do the opposite of whatever the book is doing. All right, good. The book's using 70/40. Perfect. Okay. So y minus 90, and that's equal to 1/3, and then x minus 100. Okay. I want to do the opposite of what the textbook is doing, so I can kind of show you that it doesn't matter which point you use, you're going to get the same solution either way. So anyways, let's clean this up. We're going to have y minus 90, and that's equal to 1/3 x minus, and 1/3. This could be an issue, but we're just going to put this as 100 over 3. Okay. Alrighty, and we're going to add 90 to both sides, and so maybe I see why the textbook used used 40. It's no big deal. Actually, it doesn't really matter. But anyway, so we got y is equal to 1/3 x minus 100 over 3, and then plus 90, right? Because we added 90 both sides. All right, well, let's go ahead and figure out what 90 is with the denominator of 3, because we're going to have to get a common denominator here. So it looks like 90 times 3 is 270. So we're going to rewrite the 90 as 270 over 3. Okay. And then we can finish this up with the equation y is equal to 1/3 x, and then combining like terms, it looks like it's going to be plus 170 over 3. So 170 over 3. Okay, and of course that's going to be the exact same as what the textbook has. Well, they reduced it even further, so 56 2/3. All right, so we don't actually go that far in other classes, but yeah, we can actually rewrite this. Let me move my toolbar. I don't think y'all can see my toolbar, but it's there. So y is equal to 1/3 x, and then plus 56 and 2/3. 56 and 2/3. Okay. And there we go. That is A. And let's go ahead and snip this, and we'll jump straight to B. Put this on the next page. Perfect. Alrighty. All right, so let's do B now. And let's see what the textbook is using, and we'll do the opposite. So the textbook does 90 and 80 for the point slope form. So we're going to do, okay, they're both 80 and 90. So it was y was 90. So the textbook uses this one. So I'm going to use the other one. Just wanted to note that so I can, or denote that so I can make sure I don't do that. Anyways, let's go ahead and get the slope. So m is equal to so we'll do 90 minus 80 over 80 minus 90. Okay, so this is, I won't say confusing, but it kind of sucks. So 90 minus 80 is 10. 80 minus 90 is negative 10. And so we have a slope of a negative 1. Okay. Next, we're going to put this into our point slope form. And I'm not gonna write the point slope form this time because it's on the previous page. So y minus 80 is equal to my slope, which is negative 1, times x minus 90. And let me just double check to make sure that I'm not doing what the textbook is doing. Yeah, okay, good. All right, so doing the arithmetic here, we've got y minus 80 is equal to a negative x plus 90. And then we're going to add 80 to both sides. So we're going to have y is equal to a negative x plus 170. Okay, and that is exactly what the book should have. Negative x plus 170 we see here. Okay, and it's interesting. Let me see what the textbook is doing. Oh, interesting. Okay, so let's go ahead and okay. So this graph goes with a, and let's do this. Put this and put a plus page, and I guess instead of just putting the equation on there, or not the equation, but instead of putting the graph on the page all by itself, I'm also going to show the textbook work. Uh, that way, again, you have both. I did the opposite of what the textbook did, so you get it from both sides. So that's good. Okay, and luckily for us, B is over 2 pages. Okay. All right, so using a calculator for linear correlation and regression. Um, I'm gonna just go ahead and snip this and put it on there. I'm not gonna go over it though because um, I don't I don't like the fact that it is super. I won't say super expensive, but the Texas Instrument calculators that um, every school uses and needs and stuff. I mean, when you're in high school and you have access to it, well, okay, that's cool. But when you are a broke college student and you don't have access to it, then it's not as cool. And what I mean by that is I don't expect my students to spend $150 on a calculator. So we're going to put this here just for fun, but you don't expect this on the test. Right. I say this as a broke college student that always had to borrow a calculator just for my college algebra tests. Um, Keep in mind, I wasn't starting out as going for a math degree, so I didn't have a calculator. But once I was determined to get a math degree, obviously I got a calculator. But I'm assuming many of you do not, or are not rather, getting a mathematics degree. Okay, so example 5, we're going to look at using linear regression line to predict data values. So we're going to try and predict some values here, and this is I mean this isn't really far fetched from what people actually do with linear regression models. Alrighty, so uh, example 5 reads. The following data set from the introduction represents the time that we have the time students spent studying versus the grade they earned. Of course, this is from the beginning. All right, so in example 4, we got the regression line. Y is equal to 0.44x plus 47.97. And again, as you can read, that's from example 4 using a calculator. So to predict the grade students earn on the exam for the given time spent, 70, 110, and 95. So this is just a prediction of what's a teacher can expect students to make on a test given how long they studied. Okay, and it's a prediction. It's not set in stone. It's not gospel. It's just a prediction. And A wants 70 minutes. B wants to know 110 minutes, and C wants to know 95 minutes. And the way we do this is pretty darn simple. So 70 minutes. If All right, so let's erase this and try to explain this a little bit. So looking at this, we have our equation. Okay, this equation was generated using a calculator on example 4. Um, but we have y is equal to 0.44x plus 4797. Okay. Well, we're going to, y and f of x, they're essentially interchangeable. Okay. So I'm going to go ahead and rewrite it as f of x is equal to 0.44x plus 4797. Okay. Now it's very important that I do this because I want to get you guys accustomed to the notation, because notation is very important in mathematics. So I rewrote it as f of x. So when I want to do a, it wants to know 70 minutes. I'm going to write this as f of 70. Okay. And what I'm going to do is I'm just going to plug 70 in for x, and that's it. So I'm just going to plug 70 in for x. So I'm going to say 0.44 times 70 plus 4797. And putting this into the calculator, it's 0.44 times 70 plus 47.997. We get 78.77. So if you spend 70 minutes studying, you kind of assume that you might make somewhere around a 78.77, or a 79. Okay. And that's how you do all of them. So I'm gonna go ahead and write these all out real quickly. F of 110, and then I'll put it in the calculator. So f of 110 is just going to be 0.44 times 110 plus 4797, and we'll put that solution down here in a minute. And then f of 95, okay, so let's do 110. And of course, I've already got the equation in my calculator, so I'm just going to go back and change the 70 to 110. We end up with a 96.37, and then 95, 89.77. And that's it. There's nothing else to it. Just plug in those values and for x, and then you can figure out, kind of predict what a model is saying. And that concludes today's lecture.